At the beginning of this module, first thing we're going to do is go through our ME12 midterm number 1. This was the first exam assigned on the 30th at 8 a.m. and due initially by 4 p.m. We did extend this and actually made it a 12-hour time slot and went from 6 a.m. to 6 p.m. to accommodate everyone's schedules. We'll discuss that in a little bit, but that was a little bit too much time for this exam. This exam was originally designed to be an in-class exam for 90 minutes. So for midterm number 2, we will likely either shorten this time frame, so it's no longer a 12-hour from 6 a.m. to 6 p.m., but a shorter time frame, or add another question to it. So let's take a look here at our statistics. So the class average for this exam was just over 84%. So I have all the statistics right here, and this is based out of a 20-point scale. And if we're looking at percentages over here, I now have given here our bell curve here. So we can see we're at 84.47 for our mean. And again, this was designed as a 90-minute time slot exam. For the second exam, I'm going to either be adding a problem or shortening the time slot. 12 hours is a little bit too much time for these two questions for this exam. So let's take a look at our first question here on the exam. The first question tells us that we have some boy A moving a straight line away, so that lets us know the direction, from the building at a constant speed. So we're dealing with a constant speed here of 4 feet per second. So this is for our boy A right here. At what horizontal distance, so we're searching for this distance D, must he be from C right here in order to make the catch if the ball is thrown at a horizontal velocity of v sub c is equal to 10 feet per second. So it tells us our direction right here and our magnitude of that velocity of the ball itself. Also, they want us to determine the relative speed of the ball with respect to the boy A at the instant the catch is made. So now that we've read through the problem statement, understand what they've given us in the diagram and the wording and what they're asking us to solve for, our next step is to create our setup page. So I use the same diagram right here. We have our C, the velocity at C right here. We have the boy over here at A, the velocity at A over here, this distance between where it's thrown from to where it's caught, and the height difference right here from where it's released to where it's caught as well. I write out all my givens down here. Velocity of A, 4 feet per second. Velocity of C, 10 feet per second. My S sub Y here is 20 feet. Looking for the distance D in the horizontal direction from C that A must be to catch the ball. So as we begin our solution here, we want to break things down in terms of our X and our Y components. So if we're looking at just our X direction here, we can start with our general kinematic equation that S is equal to S naught plus V naught T. So position is equal to your initial position plus your initial velocity times time. And again, this is in the X direction here. So if we're talking about point C up top here, we can see that our position X that we're looking for here in our X direction that we're looking for right here is equal to our initial position, which this starts right here at work. We're considering our origin here, or our X of 0 here, so our S naught or X naught is 0. And they tell us that our initial velocity is given in the problem statement. Our velocity at C is equal to 10 feet per second there, times time. So now we have this relationship here. X is equal to 0 plus 10t in order to solve for our position in the X direction here when he catches the ball. So now let's take a look at our Y direction here. So the Y direction, our ball is thrown from up top here and caught down here. So if we're talking about our final position here, so our initial position is here, our final position is down here. If this is our initial position at 0 up here, and we're considering our Y positive going up, then our final position down here would be a negative 20. So if we look at this here, we have a negative 20 for our final position here. Our initial position where it's released from right here is going to be 0, plus our initial velocity. Well, if we're talking about the Y direction here, it doesn't have a Y component to velocity. So our initial velocity in the Y direction is going to be 0, plus our 1/2 AC. So acceleration due to gravity is 32.2 feet per second squared. But again, this is going to be negative because we've considered our y positive going in the upward direction there, times our t squared. So we look at this, and our only unknown in this is our t. So we can solve this for time. When we do that, we find that our time is equal to 1.1146 seconds. Now with this value for time, we can take this, plug it back up here for our t value there, and when we do that, we can solve for that distance here. So we do that there, and we find, when we plug our time value back into that equation for our x direction, our distance is equal to 11.146 feet. And that is our d distance right here, position of boy A, the distance he is away from point C when he catches the ball. So the other thing that they'd ask us to solve for was the velocity of the ball. So if we want to calculate the velocity of the ball, again, I'm going to break this down in terms of our x direction and y direction separately. So let's just take a look at our x direction. Well, the velocity of the ball in the x direction, we know, given to us in the problem statement, it's v sub b, launched right here in the x direction at 10 feet per second, and the velocity in the y direction here is going to be based upon this kinematic relationship here, where v is equal to v naught plus act. So v is your vby, the velocity of the ball in the y direction. This is equal to our initial velocity in the y direction, which is 0. It only has an x direction component to begin with, plus our ACT, again, according to our chosen coordinate system, is a negative. It's going in the negative y direction of 32.2, times our time value that we solved for on the previous page, so we can plug that guy in down here. And when we do that, we find that our y direction for our velocity of the ball is equal to negative 35.89 feet per second. So we now have our x component and our y component. So here's our x component up top here for the ball, and here's our y component down here for the ball. So I rewrite my velocity components in the x and y direction for the ball at the top of the next page of my solution here. And now what we're going to take a look at on this page is our relative velocity. So recall our relative velocity general equation here. The velocity of b relative to a is equal to the velocity of b minus the velocity of a, where we now have an expression from the components up top here for a vector for velocity b, which is 10 in the I hat direction, which is our x component, minus 35.89 in the j hat direction, which is our y component over here. Again, notice the sign convention going our negative y direction. And our velocity at A here is given to us in the problem statement is simply 4 acting purely in our x direction. So 4I hat is our vector for our v sub A. So if we take a look here now, we can do our relative velocity equation. We can plug these two back into our governing equation up here. And when we do that here, we find that the velocity of b relative to A is equal to, we plug in our velocity of b vector here, and we plug in our velocity of a vector here. Pay attention to our unit vectors in this, I, j, I, combine like terms in that, so velocity of b relative to a, once we combine our 10I minus 4I here is 6I, and there is no other component in the j, so it's negative 35.89 in the j hat direction. So this is our velocity vector right here for b relative to a. If we were to want the magnitude of this here, we take the square root of the sum of the squares right here. So v sub b relative to a is equal to the square root of 6 squared plus 35.89 squared. And we do that there. Magnitude of our velocity vector is b relative to a is equal to 36.4 feet per second. Problem 2 from our exam right here. So in problem 2, the roller coaster car and a passenger have a total weight that they give us is 600 pounds. And starting from rest, so we know the initial velocity is 0, at A, travel down a track that has the shape shown here. So we have an expression for the shape of the track here. They want us to determine the normal forces on the track of the car when the car gets to this point B down here, where it has a velocity that we know of 15 feet per second. They tell us to neglect friction and the size of the car and passenger. So they give us a lot of information between the initial given diagram here, so we can also see we have our distances between A and B being the ground, the distance between A and B horizontally and vertically, and a lot of information given in the word problem itself. So now that we've read through that, understand what they've given us and what they're asking us to solve for, we can create our setup page here. On our setup page here, we see we have this expression for y is equal to 40 times the cosine of pi over 40x. We have our weight given to us as 600 pounds. Initial velocity is 0 because it starts from rest. And our velocity at B is 15 meters per second. They want us to determine the normal force of the tracks on the car when we're at point B over here, where it has a velocity that's known as 15 feet per second. We're making the assumption that there's no friction and we're neglecting the size of the car and passenger. So again, here's our point A at the top up here. There's our Y direction. There's our X direction there. Here is the distance between A and B horizontally, distance between the ground and B, distance between B and A vertically. So before we begin our solution, what I like to do is draw out my free body diagram. So what I've done here is simplified our car going down the roller coaster over here with this rectangular box over here. And I know that we're having a normal force coming up from the track pushing onto the cart. And I know we're having a weight force acting down here in our negative y direction here of 600 pounds. And what I want to do is calculate our angles in order to do our equations of motion for this problem. So what I'm going to talk about next here is how we come up with this 72.34 degrees here between the angle of our normal force on the box and our weight force here, and that comes from this given equation here relating our x and y by the shape of the curve of this roller coaster here, that y is equal to 40 times the cosine of pi over 40 times x here. So if we take a look at our relationship here for our y, for our curvature of our roller coaster here, so y is equal to 40 times the cosine of pi over 40x. So if we take the derivative of this with respect to x, so we get our dy dx, we realize that our y over our x here is the same as our opposite over our adjacent here, so the tangent of this angle, our theta term here, is equal to y over x, in our case dy dx here. So what we can do is, if this right here is equal to that, we can use this in order to solve for our theta term. So we take the derivative of dy dx, this becomes 40 times pi over 40 times negative sine of pi over 40x. So we can see here our 40 right here cancels our 40 in the denominator there. We're left with our dy dx is equal to our negative pi times the sine of pi over 40x here. So we know that at point B, our x is at 20. So with a value of x of 20 here, we can plug in an x of 20 right there, and we end up with 20 pi over 40, or a pi over 2. So now we can say, okay, the sine of pi over 2 becomes 1. This reduces down to just a negative pi here now for our dy dx. So dy dx is equal to negative pi, and if we plug that in and solve for our theta, theta is equal to the inverse tangent of our dy dx, which is a negative pi here, or theta is equal to negative 72.34 degrees. So continuing on with a little bit more trig here, what we want to do now is break down our weight component based upon that angle we just solved for, our theta, in terms of its n and t components here. Specifically, the n component is what we're interested in here. So again, remember sine, cosine, tangent, so, ca, toa here. So if we want to deal with our n term here, and we got a known value in our hypotenuse, and we're looking for our adjacent over here, we can say adjacent and hypotenuse here. Okay, we're dealing with our cosine term. So the cosine of our theta, which is this angle right here, is equal to our adjacent over our hypotenuse. So our cosine of 72.34 degrees that we just solved for is equal to our adjacent n over our hypotenuse of negative 600. We can then solve this for n. N is equal to negative 600 times the cosine of 72.34 degrees. So from this point here, now that we have our angles, we've done out our trig here, we know what our theta terms are and our n components of our weight force, we can now take a look at point B when our car on the roller coaster is at point B. So we recall our general curvature equation here for the shape of the roller coaster is y is equal to 40 times the cosine of pi over 40x. Now again, we just did this, but if we take the derivative of y with respect to x, we end up with negative pi times the sine of pi over 40x here. So again, this is where we then found our angle right there, our theta term, by taking the inverse tangent here of a negative pi term that we just did this. So we now have that angle. So at point B, we know that our x is equal to 20 feet given in our initial diagram, so we can plug this in over here. So dy dx is equal to negative pi times the sine of 20 pi over 40 here. When we plug in our value of 20 for x, goes right there. So this reduces down now. We say that negative pi times the sine of pi over 2, which is 1, is negative pi. So again, that's where this came again when we were calculating our theta term right there. We can do this one more time, take the derivative of y with respect to x again, and we can get d squared y over dx squared. So we do that now, and this becomes negative pi squared over 40 times the cosine of pi over 40x right there. And again, we know that x is equal to 20. We can plug that in for our x value there. So we end up with still pi over 2, but now the cosine of pi over 2 becomes 0. So if that becomes 0, this whole term becomes 0, so our dy squared over dx squared term here is 0. From this here, now that we have our dy dx and our dy squared dx squared, the reason we needed this is because we wanted to get a radius of curvature. So recall our radius of curvature equation given right here. Rho is equal to 1 plus dy over dx squared, all to the 3/2, divided by d squared y over dx squared. Now we can plug in our known values we solve for dy dx and d squared y over dx. While we have our top value over here, this simply becomes 1 plus pi squared to the 3/2 power. All over, though, our bottom term, our d squared y over dx squared, is 0. So 1 over 0 becomes infinity. So our radius of curvature, our rho, is equal to infinity. So now we can move on to our solution, page 3, where we go back to our free body diagram we drew at the beginning of our problem here. And what we're going to do is look at the sum of our forces in the normal direction. So here's our free body diagram over here. We can see we have our normal force of the track pushing up on the car. We have our angle that we solved for, and we have our weight force acting down here. So we recall Newton's second law, the summation of forces equal to mass times acceleration. For our case here, summation of forces in the n direction is equal to mass times acceleration. We're considering this to be positive n direction here, going up right there. We recall we have our angle here of 72.34 degrees based off of our inverse tangent of negative pi. So we have that to break down our weight force. So if we're talking about what are our forces acting in our normal direction here, we have this normal force from the car, from the track pushing on the car, and we have a component of our weight force acting in our negative n direction there. So we already did our trig out and broke this down. This is 600 times the cosine of 72.34 degrees right there. So there are our forces from our free body diagram acting in our normal direction. And our mass is equal to our weight divided by acceleration due to gravity, or 600 pounds divided by 32.2, which is 18.36 for our mass. Our acceleration we can calculate from our relationship of v squared over rho, where our rho is a radius of curvature that we solved for on the previous slide here to be infinity. Our v is our v sub b, which is given to us as 15. So what we have is 15 squared over infinity. Anything divided by infinity becomes 0, so our acceleration becomes 0. So now we can go back up to our equation for motion here to solve for our nt, and we have that summation of forces in the n is equal to mass times acceleration. So our summation of forces in the n are right here, which is our nt minus 600 times the cosine of 72.3 is equal to our mass, which is weight divided by gravity, times our acceleration, which was 15 squared divided by infinity, which ends up going to 0 here. So this whole side becomes 0 over here now. So we're just left with the fact that nt minus 600 times the cosine of 72.34 is equal to 0, or nt is equal to 182 pounds.